Hi everyone, my name is Modi. I'm an engineer on the server LLVM team at Meta, and today I'll be talking about examining and mitigating the performance impact of C++ exceptions on a non-exceptional path in LLVM. First off, let's start off with some background. How C++ exceptions are modeled in LLVM. C++ exceptions are synchronous, which means they can only occur at specific points. In this case, they can only occur from calls. Calls that can throw exceptions are modeled in LLVM by the invoke instruction. Like a normal call, if the call succeeds normally, it goes along a non-exceptional path and falls through. However, if an exception does occur, there's a separate label here that contains an edge to something known as a landing pad. This is code that gets executed if an exception does occur. The combination of the CFG edge and the landing pad is what constitutes the IR cost for C++ exceptions in LLVM. The addition of these landing pads hampers inlining. Here, I have a very small example of a very simple landing pad that only calls a destructor. The costs are the inline costs for each specific instruction. As you can see, taking it all together, this single landing pad has a cost of 45. In O3, the max default budget is 250. So even a single landing pad, a very simple one as well, can eat into the cost quite considerably. More complex landing pads, such as destroying a vector of objects, cost up to 125, which is half the budget of the O3 inlining. Moving on, the addition of landing pads can lead to more conservative memory aliasing. Capture tracking, used in general alias analysis, has a limit on value usage. In the code snippet below, the default max uses to explore is initially set to 20. If a value is used more than 20 times, the pointer is considered captured. Landing pads introduce additional uses, which means this limit gets broken more often, leading to more conservative memory aliasing. As an example, when building Clang with exceptions versus without exceptions, we end up with 34% more captured pointers, leading to 7% fewer instructions hoisted by loop invariant code motion. The last thing I'm going to talk about is how landing pads affect register allocation. In the code snippet below, we have an object that needs to be destroyed if any single one of the calls below throws. Each call has a CFG edge to the landing pad, therefore, to destroy object. What that means is that if object is placed in a non-volatile register or on the stack in the landing pad, it must be there before every call. This lowers register allocation flexibility because, for instance, in the loop, may throw 1 might prefer object in a non-volatile register, but may throw 2 may prefer it be on a stack. Instead, because of this additional landing pad and this additional CFG edge, it has to be in a consistent place in all 3 sites. Taking all this together, we actually see a performance impact comparing without exceptions versus without exceptions on a non-exceptional path. So here we have Clang building scalar evolution.cpp. We see that if you build Clang without exceptions versus building Clang with exceptions, Clang is 1.7% faster without exceptions than with exceptions. Similarly, on MySQL link bench, without exceptions, it's 0.5% faster. Next, I'm going to talk about how to mitigate the costs. And specifically, the approach we're going to look at here is lowering the number of landing pads needed. Without the landing pads, there's no cost associated with them. The first strategy is to remove the largest propagator of exceptions. The largest bottom-up propagator of exceptions is actually operator new. However, not many programs can or expect to recover from out of memory, but they still have to pay the cost of landing pads associated with them from the possibility of an exception happening from this location. In order to address this, I implemented a new Clang frontend flag, fNewInfallible. This expresses to the optimizer that operator new cannot fail and terminates if an exception occurs, meaning that landing pads do not have to be generated upstream along its callers. Doing this results in a 9.3% increase in functions without exceptions in a Clang thinLTO build. A second approach in a similar vein is to improve NoUnwind attribute propagation. Calls outside of a translation unit, unless they're annotated, have to be considered potentially throwing. We don't know if they throw or not, so we have to be conservative for the sake of correctness. However, if you can propagate what these functions actually throw across translation units, in something like thinLTO helps eliminate this pessimistic analysis. The second part then is to propagate these attributes during thinlink. thinLTO summaries are used to propagate NoUnwind across the call graph of the entire program. This is already been committed, and you can turn on by passing the flag disable thinLTO func attrs equals 0. the plan is to turn this default on because this is just general goodness, but we're still testing to make sure that all the correctness and reliability issues are there. Doing this results in a 9.9% increase in functions without exceptions in the Clang than LTO build. Taking these together, FNU infallible and thin link propagation leads to performance improvements along the non-exceptional path. If you recall, Clang, when building without exceptions, was 1.7% faster, building scalar evolution. Now, with FNU infallible thin link propagation, that gets cut in half, because doing so results in a 0.8% increase in performance. On some of our own search backends, like meta search, we also see a 0.2% performance increase. And similarly for meta feed, we'd see a 0.4% increase. Now, these numbers are very small. So specifically for the meta feed number, the number is not, unfortunately, conclusive because of measurement difficulties at this level. Looking forward, there are additional ways to lower the number of landing pads needed. Additional exception propagators could be annotated, just like operator new gets annotated, notably those in libstud C++. Another approach can also be taken, which is lowering the cost of having the landing pads themselves. One approach is to use outlining for exception-only code into cold code early. This means that it no longer has to impact the inline cost model, and therefore the costs to inlining that was described before no longer exists. All right, thank you. If you have any questions or comments, please leave them on the video or find me at the conference. Otherwise, thanks and have a good one.